Tonight, on Z Science, we'll drift together into the quiet corners of the universe. Whether your mind is racing or your body just needs rest, these gentle stories of science are here to help you slow down and drift off with ease. But before we begin, I would love to know where in the world you are listening from, and what time it is where you are right now. Are you winding down under city lights, or nestled somewhere quiet and dark, perhaps with a cup of something warm? If you enjoy these sleepy explorations, I would be so grateful if you gave the video a little like and tapped that subscribe button. It helps more sleepy scientists like you find their way here, and it means I can keep making more of these soft starlit journeys for you. Now, I do hope this video is not too interesting though. If it does accidentally keep you awake, at least you will come away knowing a bit more about how our universe works. Not such a bad trade, really. So settle in, close your eyes if you like, and let us take a slow, thoughtful wander through the story of light and why it is in such a hurry to get anywhere at all. Light is one of those things we all think we understand until we actually try to explain it. You flip a switch, and there it is. It fills the room, lets you see your cat's judgmental stare, and makes your phone screen glow long after you swore you would put it down. But what is it really? Is it a wave, a particle, a ghost, a cosmic courier with a very strict delivery schedule? The short answer is yes, and also sort of. Let us take a nice slow wander through what light actually is. Because before we can understand why it has a speed limit, we first need to understand what is actually doing the speeding. First, let us talk about photons. They are the tiny packets that make up light. Imagine them as little messengers zooming through the void at the fastest speed allowed by the universe. But these messengers are strange. They are not particles in a traditional sense, like marbles or peas. They do not have mass. They do not rest. And they definitely do not follow the usual rules. Now, here is where it gets fun. Photons are also waves, but not waves like ocean waves or wavy hair. They are electromagnetic waves, vibrations of electric and magnetic fields that oscillate at right angles to each other and to the direction they are moving. Yes, it sounds like a physics yoga class, but the mental image is quite elegant. Two fields dancing through space together, locked in a perfect rhythm. These waves do not need a medium to travel through. That is important. Most waves, sound waves, water waves, even the wave you give your neighbor from across the fence, needs something to move through. Sound needs air. Water waves need, well, water. But light just goes. It travels through the vacuum of space without a problem. That is why we can see the sun, which is over 90 million miles away. Its light has traveled through the emptiness of space to reach us without a single rest stop. And it does not just come in one flavor. The light we can see, what we call visible light, is only a tiny part of the electromagnetic spectrum. Imagine a piano that stretches for miles. Visible light is just a handful of keys in the middle. On one end of the spectrum, we have got radio waves, long lazy undulations that can stretch for miles. On the other end, we have got gamma rays, sharp, high-energy spikes that can pass through almost anything and are usually found in the company of exploding stars and nuclear reactions. In between, you have got microwaves, infrared, which your TV remote uses, ultraviolet, which gives you sunburns, and X-rays, which can see through your bones but somehow never find your missing socks. But despite all these differences, all these forms of light move at the same speed in a vacuum. roughly 299,792,458 meters per second. That is just under 300,000 kilometers every single second. A number so big, it feels like nonsense. It is like saying, "How fast is that?" And the universe replies, "Yes." To put it in bedtime terms, if light were a runner, it could jog around the entire Earth more than 7 times in a single second. Not bad for something with no legs. But here is something else to keep in mind. Light does not always go that fast. In a vacuum, it has got a clear track and no traffic. But when it passes through something like water, glass, or even diamond, it slows down. Not because it is tired, but because it is interacting with the material's atoms. It is a bit like walking through a crowded room. You are still heading in the same direction, but there is a lot more bumping and weaving to do. That slowing down is what causes refraction, the bending of light when it moves from one material into another. That is why a straw looks bent in a glass of water, or why a diamond sparkles so brilliantly. It is all about how light's journey gets delayed, rerouted, and scattered. But here is the twist. Even though light slows down in these materials, individual photons still travel at the same speed between atomic interactions. They are just taking a more complicated path, like someone trying to speed walk through a dance floor full of enthusiastic uncles at a wedding. Now, let us talk for a moment about color. When we look at a rainbow or a prism or the weird oil slick in a puddle, what we are seeing is light split into its various wavelengths. Each color of visible light has a different wavelength. Red is long and lazy. Violet is short and twitchy. But all of them are still photons, still electromagnetic waves, just vibrating at different frequencies. Your eyes have special cells, cones, that are tuned to specific ranges of those wavelengths. That is how you see color. It is not that the apple is red. It is that it is reflecting the wavelength we interpret as red while absorbing the rest. In a way, color is just your brain's best guess based on which vibrations make it to your retinas. And as if all this were not already wonderfully strange, light also has no rest mass. That means, unlike you or me or your slightly judgmental cat, it does not need energy to move. It always moves. It has no choice. If a photon were to stop, it would not just be taking a break. It would cease to exist. It is motion or nothing, all or gone. That is not just poetic. It is physics. So, we've got these massless packets of energy that behave like both waves and particles, that travel at a universal speed, that can interact with atoms, bend around corners, and bounce off surfaces, all while delivering the very experience of sight and color to conscious brains like ours. And that is just scratching the surface. But for tonight, let us hold on to this image. Light as a restless traveler made of no substance but energy, never pausing, never sleeping, always tracing the outlines of everything we know. It shows us the stars, the faces we love, the pages of our favorite books. And it does all this while obeying one of the most curious rules in the universe. A speed it will never exceed and never fall below dot. Light is not just what helps us see. It is how the universe whispers its story into our eyes. Let us take a gentle step back in time, long before satellites and lasers, before physicists had high-tech tools to measure the universe's secrets. Imagine a world lit only by fire and stars, where understanding something as elusive as light speed was not just difficult, it seemed almost absurd for most of human history. People believed that light moved instantaneously, It was just there. You lit a candle and the room lit up. The sun rose and the world turned golden. No waiting, no delay. It seemed obvious. Why would anyone think otherwise? Even the ancient Greek philosopher Empedocles, one of the few to suggest that light might have a finite speed, was not taken very seriously. Aristotle, whose opinions had the unfortunate habit of sticking around for centuries, thought light was instantaneous, and that was that. Case closed, curiosity shelved. But then came Galileo. Now, Galileo was not one to accept things just because someone important said so. He liked to poke things, drop them off towers, and point telescopes at moons. And around the year 1638, he tried to measure the speed of light in what might be the most adorably optimistic experiment in history. The idea was simple. Galileo and his assistant each took a lantern, covered it, and stood on hilltops about a mile apart. Galileo would uncover his lantern, and as soon as his assistant saw the light, he would uncover his in return. Galileo would then measure the time between sending the signal and seeing the return flash. Now, even under the best of circumstances, this experiment was ambitious. The human reaction time alone is about 1/4 of a second. Light, meanwhile, takes less than a 10,000th of a second to travel a mile. It is like trying to measure the speed of a bullet with a sundial. Still, you have got to admire the effort. Galileo unsurprisingly concluded that if light did have a finite speed, it was far too fast for him to measure, which was true. But at least the question had been asked. Fast forward a few decades to a Danish astronomer named Ulrichmer, who, in 1676, would accidentally stumble upon the answer by watching something quite far away. The moons of Jupiter. Rachmer was tracking the orbit of Io, one of Jupiter's many moons, which zips around the gas giant like a cosmic clockwork. By carefully observing when Io disappeared behind Jupiter and when it reappeared, he noticed something odd. The timings were not always the same. Sometimes Io appeared a little late. Other times, it was a bit early. At first glance, this might seem like bad luck or bad measuring, but Rachmer had a brilliant thought. What if it was not Io that was being inconsistent, but us? What if the delay was caused by the fact that Earth was sometimes farther away from Jupiter and the light from Io had farther to travel? And just like that, the idea of light having a measurable speed began to take real scientific shape from these timing discrepancies. Rachmer estimated that it took light about 22 minutes to cross the diameter of Earth's orbit, a distance we now know to be about 186 million miles. That is not too shabby, considering he did not have access to accurate distances or modern clocks. His estimate was not perfect, but it was revolutionary. It told the world that light takes time. Not much, but enough to matter. Later, in the early 1800s, a physicist named Hippolyte Fizeau decided to try something more earthbound. His method involved a beam of light, a rotating toothed wheel, and a mirror placed several miles away. Here is how it worked. The beam of light passed through a gap between the teeth of the wheel, traveled to the distant mirror, and bounced back. If the wheel was spinning slowly, the returning light would pass through the same gap and be visible. But if the wheel spun faster, the returning light would hit a tooth instead of a gap and be blocked by adjusting the speed of the wheel. Fizeau could figure out the point at which the light beam was completely extinguished, meaning it had just enough time to travel to the mirror and back while the wheel rotated half a tooth's width. Using the known distance and the wheel speed, he calculated the speed of light to be about 193,000 meters per second. That is not far off the modern value. especially considering he was using mirrors, gears, and a whole lot of cleverness. Later still, another scientist named Leon Foucault refined the technique using rotating mirrors instead of toothed wheels, improving the precision significantly. He showed not only that light has a finite speed, but that it actually moves slower in water than in air. A critical clue that light interacts with materials in ways that affect its velocity. But perhaps the most iconic name in all of this is Albert Michelson. In the late 1800s, Michelson took Foucault's method and fine-tuned it to a level of accuracy that no one had achieved before. He used long tunnels, carefully aligned mirrors, and incredibly precise timing to produce results that stunned the scientific world. His efforts earned him the Nobel Prize in Physics in 1907, making him the first American to receive the honor. Not a bad reward for chasing beams of light around with mirrors. Today, we have even better tools: lasers, atomic clocks, satellites. We have even defined the meter itself based on the speed of light. Since 1983, the meter has been officially described as the distance light travels in 1/299th, 792,458 of a second. In other words, we have flipped the equation. We no longer measure the speed of light. We use it as a standard to measure everything else. But it all started with people watching moons, spinning wheels, and wondering whether the universe might be slower than it looks. And maybe that is the quiet beauty of it. The speed of light is not just a number. It is a story of curious minds, imperfect tools, and elegant persistence. A tale told across centuries from mountaintops and observatories and distant orbits. Proof that even the fastest thing in the universe could not outrun human curiosity. And so the story of light's measurement is not just about physics. It is also about people. Galileo with his lanterns and his stubborn belief that the world could be tested. Rachmar with his sharp eye for patterns in the night sky. Fizeau and Foucault with their clever contraptions of wheels and mirrors. Michelson with his relentless pursuit of precision. Each one of them nudged humanity a little closer to the truth. Each one of them showed that the universe, however swift, could still be caught, studied, and understood. That is what makes the history of lightspeed so quietly inspiring. It is not just that we know the number today. It is that we earned it. Step by step, failure by failure, correction by correction. We proved that, even in the vast silence of space, curiosity is louder. So, now that we have met our speedy little photon friend and followed the long, curious journey to measure its pace, let us ask the question that really keeps physicists up at night. Why does not light just go faster? After all, it seems like a bit of an arbitrary number. Why 299,792,458 meters per second? Why not a nice round 300 million, or 500 million, or just infinite? Why does light, this ethereal, massless bundle of energy, have to obey a cosmic speed limit? To understand this, we need to take a calming stroll into one of the most elegant and mind-bending parts of physics, electromagnetism. More specifically, we are going to talk about a man named James Clerk Maxwell in the 1860s. Maxwell took everything scientists knew about electricity and magnetism at the time, Benjamin Franklin's lightning rods and Michael Faraday's coils and magnet sand, turned it into 4 beautiful mathematical equations. These are known, somewhat unimaginatively, as Maxwell's equations. They describe how electric and magnetic fields interact, change, and move. Now, you do not need to worry about the actual equations. No one is going to quiz you at bedtime. But here is the dreamy part. When Maxwell combined these equations, he discovered something extraordinary. They predicted a type of wave, an electromagnetic wave, that would naturally emerge whenever electric and magnetic fields wiggled in just the right way. And this wave would always travel at a specific speed. When he did the math, plugging in the known values for electric and magnetic constants, he got a number. That number, you guessed it, 299,792,458 meters per second. Maxwell was stunned. He had found a number, a fundamental speed buried deep within the laws of electricity and magnetism. And the kicker, that number matched the best available measurements for the speed of light. This was not just coincidence. It was a revelation. Light, Maxwell realized, was an electromagnetic wave, a self-propagating ripple of electric and magnetic energy, zooming through the void at a speed dictated not by chance, but by the very structure of the universe. Let that sink in. Light speed is not just a habit. It is built into the equations that govern the fabric of reality. It is not like the universe randomly spun a dial and landed on that number. It is more like the universe had to work this way. If electric and magnetic fields exist, and they definitely do, then light must travel at this speed. So that is part of the answer. Light goes the speed it does because that is the only speed electromagnetic waves can travel in a vacuum. Anything faster or slower would break the laws as we understand them. But now, let us go one step deeper. Why cannot anything go faster than that? After all, in everyday life, we are used to speed being kind of optional. If your car goes 100 kilometers per hour, it can also go 110 if you are feeling daring. But with light, there is no upgrade, no speeding ticket, just a hard stop to find out why. We need to call in someone you have probably heard of, Albert Einstein. In 1905, Einstein published his special theory of relativity, and with it, he changed everything. One of the key postulates of special relativity is this: the speed of light in a vacuum is the same for all observers, no matter how fast they are moving. That might sound tame, but it is actually bananas. Imagine you are on a train moving at 90% the speed of light. Very impractical, but excellent for thought experiments. You turn on a flashlight. You might expect that the light from your flashlight would appear to move faster for someone standing on the platform. After all, the train is already moving, and you have added the flashlight beam on top. But no. Both you and the person on the platform would measure the speed of that light beam as exactly the same. 299,792,458 meters per second. Not a hair more, not a flicker less dot. To make that possible, reality has to bend itself around this rule. Time slows down, lengths contract, mass increases. The universe changes the way it ticks to ensure that no one, no matter how fast they go, can ever observe light speeding up or slowing down. And if you, a brave astronaut, tried to accelerate to the speed of light, you would run into a problem. As you get faster, your mass increases. Not in the eating too many cookies sense, but in the sense that you require more and more energy to go just a little bit faster. As you approach the speed of light, your mass trends toward infinity, and that means you would need infinite energy to reach it. Infinite energy is a pretty tall order, even for the most ambitious traveler. And so, no matter how hard you try, you can get close, but never quite there. You can chase the light, but you will never catch it. That is why the speed of light is not just the speed of light. It is the cosmic speed limit, the upper bound on how fast information, energy, or anything with mass can travel through the universe. It is a barrier, a boundary, a fundamental part of space-time itself. And here is a peaceful thought. If the speed of light were not limited, everything would fall apart. Causality, the idea that causes happen before effects, would break down. You could theoretically see an effect before the cause, or send information backwards in time. It would be chaos, time travel, paradoxes, and a serious headache for logic. Instead, the universe protects us from that kind of nonsense with this beautiful little speed cap. It keeps things ordered, predictable, calm. No matter what else changes, the speed of light stays the same. So the next time you watch a sunset or marvel at the stars overhead, remember those beams of light did not just happen to arrive. They followed a rule, one written into the very bones of physics. A rule that says, this far, no farther. A limit, yes, but a limit that gives the universe structure, stability, and beauty. Light does not go faster because it cannot. Not because it is weak or lazy, but because it is perfect exactly as it is, bound to a speed that keeps time flowing forward, keeps causality intact, and lets us understand the world in a way that would otherwise be impossible. And honestly, for something that zips across space at nearly 300,000 kilometers per second, I think that is a pretty graceful pace. And maybe, when you think about it in this way, the speed limit of light is not a restriction at all. It is more like the rhythm of a song, steady and unwavering, keeping the entire universe in time. Without that rhythm, the music of existence would collapse into noise. With it, we have harmony. With it, we have order. With it, we have beauty. Albert Einstein had a gift for flipping reality on its head and making it seem obvious in hindsight. Like the universe had been whispering secrets all along and he was just the first to actually listen. When he introduced his theory of special relativity in the year 1905, he did not just tweak the rules of physics, he rewrote them. At the heart of his theory was a bold statement. The speed of light in a vacuum is constant. Not just generally constant, not pretty consistent if you are not moving too fast. No, absolutely constant for everyone, everywhere, always. This might sound quaint if you are drifting off to sleep, but it breaks everything you think you know about motion and time. Let us say you are on a spaceship floating peacefully through the void. You are holding a flashlight. You turn it on. A beam of light shoots out in front of you at, say it with me, 299,792,458 meters per second. Now, imagine someone else, your co-pilot perhaps, is flying past you in another spaceship at half the speed of light. From their perspective, you and your ship are whizzing by like a blur. But when they measure the speed of that same beam of light, they do not see it moving any faster or slower. They also measure it at exactly 299,792,458 meters per second. That is weird, like deeply weird. In the everyday world, speeds add up. If you are walking on a moving sidewalk at the airport, your speed is your walking speed plus the speed of the moving belt. But with light, the sidewalk could be moving, the person could be moving, the flashlight could be moving, and the light speed stays the same for all of them. So what gives? Einstein's solution was beautifully unsettling. It is not the speed of light that changes. It is everything else. Time, space, the passage of moments, the size of things. All of it bends and stretches to preserve that one sacred number. Let us gently walk through the consequences. First, time dilation. This one is a favorite among physics students and science fiction writers alike. The faster you move, the slower time passes for you compared to someone at rest. Not just subjectively, it is a real measurable effect. For example, let us say you are on a spaceship traveling at 90% the speed of light. To you, everything on board feels perfectly normal. You eat snacks, read a book, maybe wonder why you did not pack more socks. But when you return to Earth, you might find that much more time has passed for everyone else than for you. Years, even decades. While you experienced a short trip, Earth aged without you. This is not a theory that just lives in books. We have tested it. Particles called muons, which are created high in Earth's atmosphere by cosmic rays, decay in microseconds. But when they are moving near the speed of light, their internal clocks slow down and they last longer. Long enough to reach the ground and be detected. Time actually stretches for them as they move. Next, length contraction. This is the strange twin of time dilation. When you travel at high speeds, objects in the direction of your motion appear shorter, not by optical illusion, but by physical reality. Your spaceship would literally measure shorter along its path of travel. Now, before you imagine yourself folding into an uncomfortable cube, know that this only becomes noticeable at speeds close to the speed of light. For everyday travel, cars, planes, or very enthusiastic joggers, the effect is so small it might as well not exist. But near light speed, the universe gets squishy. Then there is relativity of simultaneity, which sounds like a tongue twister, but is actually a lovely bit of mental yoga. It means that two events which seem to happen at the same time for one person might not happen at the same time for another if they are moving relative to each other. Imagine a train moving very fast. In the middle of the train, a light bulb flashes. From the train passenger's point of view, the light reaches the front and back of the train at the same moment. But from someone standing on the platform, the light reaches the back of the train first because the front of the train is moving away from the flash. Both observations are correct. Time and space are no longer universal. They are flexible, local, relative. All of this strangeness, time stretching, distances shrinking, simultaneity breaking down, it all happens to protect that constant speed of light. It is as if the universe looked at this one number and said, everything else can bend, but this must not break. It is a little like a cosmic contract. In exchange for allowing light to remain constant, the universe agrees to warp everything else around it. It is a delicate balancing act that keeps causality intact. Speaking of causality, here is a soothing thought. This cosmic speed limit is what protects our sense of before and after. Because light can only travel so fast. Information can only travel so fast. That means you cannot see an event before it happens. And you cannot send a message into the past. The light speed limit keeps the universe logical, predictable, tidy. Without it, things would get messy. You could, in theory, cause effects before their causes. You could receive a message before someone sent it. Paradoxes would pile up like socks in a teenager's bedroom. Instead, the universe gently says, "No, let us not do that. Let us have order. Let us have a maximum speed and let us make it sacred." And so, this is where Einstein's work shines brightest. He did not just describe the speed of light as a limit. He showed that it is a cornerstone of reality, the cosmic scaffolding that holds up time and space. Today, GPS satellites rely on Einstein's equations to keep your phone from thinking you are in the middle of the ocean. Particle accelerators use them to guide subatomic particles around at astonishing speeds. Astronomers use them to decode the whispers of the cosmos from distant galaxies. All of it rests on this strange but constant truth. Light has a maximum speed, and that speed is the same for everyone. So the next time you see a sunbeam falling through your window or a lighthouse flickering in the dark, take a moment to marvel at what that light represents. Not just energy, not just warmth, but the delicate geometry of space-time itself. A quiet contract written in the language of light. And no matter how fast you go, no matter how far you drift, it will always greet you at the same pace, unchanged, unwavering, and eternally on time. And if you let the thought linger a little longer, you might realize that this contract is not cold or mechanical. It is almost protective, a rule that keeps reality from collapsing into contradiction. Without it, past and future would blur together. With it, we get history, memory, and the chance to dream about tomorrow. So far, we have explored light itself, what it is, how we measured its speed, and why the universe insists on giving it such a precise and unbreakable limit. But now, let us gently pull back the camera and look at what this cosmic speed limit actually does to reality. Because once you realize that light cannot go any faster than it already does, the implications are surprisingly far-reaching and in many ways quite beautiful. Let us start with something fundamental to how we understand the universe. Time, not your kitchen clock kind of time, but the kind that ties together events, memories, and causality. Light's speed limit gives time a structure. It draws boundaries around what can influence what. It tells the universe, you may only connect the dots if there is time for light to travel between them. This idea is what physicists call the light cone. It is not a snack or a lampshade. It is a way of mapping out what parts of space-time are connected by cause and effect. Imagine this. You are standing in a field and you light a match. That tiny spark sends out light in every direction. The furthest anything can be affected by that match immediately or eventually is limited by how far light can travel from that moment onward. If someone is standing very, very far away, say 100 light years, they will not even know the match was lit until 100 years later. Now flip it. Imagine you are standing in that same field waiting for something to happen. The only events that could possibly influence you right now are the ones whose light has had time to reach you. That is your past light cone. Everything that could have possibly caused your present moment. The light cone is not just a clever diagram. It is the border between possible and impossible. If something happens outside your light cone, it is not just too far away. It is too far away in time. No signal, no sound, no whisper from that event can reach you yet. It is as if it does not exist for you. Not until the light arrives. This idea shapes our entire understanding of the universe. It means there is no such thing as instant communication, no perfect synchrony across space, no omnipresent now. Instead, every moment is local. Every now is a bit different depending on where you are. And light speed is the rule book that keeps it all consistent. Think about how this affects your view of the night sky. When you look up at the stars, you are not seeing them as they are. You are seeing them as they were. The light from the nearest star system, Alpha Centauri, takes more than 4 years to reach us. If something dramatic happened there last week, we will not know for several more years. And that is the nearby neighborhood. Look further out, and the effect becomes even more dramatic. The light from the Andromeda Galaxy takes over 2 million years to arrive. You are seeing it as it looked when early humans were just starting to figure out how to make tools. Beyond that, we see light that left its galaxy billions of years ago, before our sun even existed, and yet it feels so present. The stars twinkle, the galaxies glow. They seem right there, but they are not. They are history written in beams of light traveling at their own patient pace. This delay is what allows astronomers to be time travelers of a sort. When they look into deep space, they are not just looking far, they are looking back. Every telescope is also a time machine peering into epochs long gone. And all of this insight is possible because light does not move instantly. Its limit gives us access to the past. There is also something elegant about how this delay enforces causality. You cannot influence something unless there is time for a signal to get there. That is not just a rule, it is a safeguard. It prevents paradoxes. It is the universe's way of saying, let us keep things logical. Without this speed limit, chaos would ensue. If you could send signals faster than light, you could, in theory, send a message to your past self. You could say, do not eat that suspicious burrito. And if you listened in time, you would have no reason to send the message in the first place. That is the kind of logic loop that keeps theoretical physicists up at night, and not in a good way. But with the speed of light as a cap, those loops never happen. You cannot outrun your own consequences. Events happen in order. The past stays behind you, the future ahead. It is not just the flow of time, it is the structure of time, and it affects more than distant galaxies or imaginary time machines. It is built into your day-to-day life. Consider communication. When you make a phone call or send a text message, you might not think about light speed. But if you are talking to someone on the other side of the planet, there is a very slight delay, tiny but measurable. The signal is traveling as electromagnetic waves, often bouncing through satellites or fiber optic cables. These waves move at or near the speed of light, but Earth is big, and light, while fast, still takes time. Now, think about spacecraft. When Mission Control sends a signal to a Mars rover, it can take anywhere from 4 to 20 minutes for the message to arrive, depending on where the two planets are in their orbits. That means if the rover stubs its robotic toe on a Martian rock, the scientists on Earth will not know until nearly half an hour later. There is no real-time remote control. The rover has to be autonomous, making decisions on its own because the speed of light says, you are on your own out here. Even your favorite streaming service obeys this limit. Every pixel, every frame of your late-night documentary binge had to travel from some server across cables and switches, all moving as pulses of light, limited by the universe's built-in pace. It might sound like a constraint, but really, it is a kind of harmony. The speed of light gives us a universe where effects follow causes, where the past is fixed and the future is waiting. It gives structure to space and time. It turns an endless, featureless void into a tapestry of ordered events. And while it might seem strange to think that the fastest thing in the universe is also the thing that slows down how quickly we can know something happened, that delay, those tiny moments of waiting, are what make the universe understandable. They give us distance, perspective, a little room to think, and maybe, just maybe, a little space to rest. As we follow the trail of light and its speed limit, another gentle realization appears. This number, this seemingly arbitrary cap on cosmic velocity, does more than set boundaries. It weaves together space and time into a single, inseparable fabric. Einstein's special relativity did not just proclaim that light speed is constant. It revealed that space and time themselves are not separate threads, but are interwoven into what we now call spacetime. Let us take a soft step into this concept. In everyday life, space feels like the stage and time feels like the ticking clock. The stage is there. The clock ticks forward, but relativity tells us that these are not separate. They are deeply linked. Motion through space affects motion through time, and vice versa. You cannot change one without changing the other. Think again of the train moving near the speed of light. For the passenger inside, time flows normally. For the person on the platform, the passenger's time runs slow. That difference is not just an illusion. It is reality. It happens because both observers are slicing space-time differently. The stage and the clock are shifting together in order to keep the speed of light sacred. Space-time is not rigid. It can bend, stretch, warp. When something massive, like a planet or a star, is present, space-time curves around it. And here is where the story deepens. Einstein extended his theory of relativity into what we now call general relativity. In this grander theory, gravity is not a force pulling objects the way Isaac Newton imagined. Instead, gravity is the curvature of space-time itself. Imagine placing a heavy ball on a trampoline. The fabric dips under the weight. Smaller balls rolled across the surface curve toward the heavy one. Not because they are pulled by an invisible string, but because the surface itself guides their motion. That is space-time around a star or a planet. Light itself follows these curves. Starlight bends around the sun, creating illusions of stars being shifted in the sky. This bending was famously observed during a solar eclipse in 1919, providing the first dramatic confirmation of Einstein's theory. The speed of light remains the same, but the path it takes is shaped by the geometry of space-time. It is like walking across a hilly meadow. Your pace may not change, but the distance and the route certainly do. This is why astronomers see phenomena like gravitational lensing, where light from a distant galaxy is bent around another galaxy in between, creating arcs and rings of distorted light. Entire clusters of galaxies act like cosmic magnifying glasses, letting us peer deeper into the universe than we otherwise could. The speed of light is thus not just a limit. It is a tool for mapping the structure of reality. Every time we measure how light is bent, slowed, or delayed, we learn something about the shape of space-time itself. We see invisible matter, we weigh galaxies, we trace the unseen scaffolding of dark matter. Without the speed limit of light, without its obedience to the geometry of space-time, much of this cosmic cartography would be impossible. Now, think of black holes. These are the ultimate consequence of space-time's ability to curve. When enough mass collapses into a small enough region, space-time curves so steeply that nothing, not even light, can escape. The event horizon marks the boundary. Once crossed, all paths lead inward. Light, which normally races freely across the cosmos, becomes trapped. The speed limit is still there, but the path is so twisted that all routes fall inward. This reveals something profound. The speed of light is not simply a rule about motion. It is also the boundary between what is visible and what is hidden. Black holes remind us that even though light is fast, it is not invincible. Space-time itself can shape and redirect it, creating shadows, horizons, and mysteries that remain beyond our reach. And yet, even here, the constancy of light speed is crucial. Without it, black holes would not form as we understand them. The horizons would not exist. Gravity would not bend light in the same elegant way. The universe would lack these extraordinary laboratories where physics pushes against its own edges. Let us step back for a moment and consider how much this one constant does. It links electricity and magnetism. It gives us relativity. It sets the rhythm for time. It draws cones that map causality. It bends around stars. It hides inside black holes. It frames the very stage of existence. All of that from a single speed. It is humbling and maybe also calming to realize that something so fast and so constant is also so gentle in its consequences. It does not shout. It does not demand. It simply is. Every photon you see, every glimmer on water, every sunrise and candle flame obeys this rhythm. The speed of light is the quiet law written everywhere, never broken, never changing, and always guiding. So, when you next look at the night sky, remember that each point of light you see has traveled faithfully along space-time's curves at the only speed it knows. It has crossed gulfs of darkness, bent around stars, passed through interstellar clouds, all while keeping the same pace. In those beams, you are not just seeing brightness, you are seeing the universe honoring its most ancient rule. As we follow the trail of light and its speed limit, another gentle realization appears. This number, this seemingly arbitrary cap on cosmic velocity, does more than set boundaries. It weaves together space and time into a single, inseparable fabric. Einstein's special relativity did not just proclaim that light speed is constant. It revealed that space and time themselves are not separate threads, but are interwoven into what we now call spacetime. Let us take a soft step into this concept. In everyday life, space feels like the stage and time feels like the ticking clock. The stage is there. The clock ticks forward, but relativity tells us that these are not separate. They are deeply linked. Motion through space affects motion through time, and vice versa. You cannot change one without changing the other. Think again of the train moving near the speed of light. For the passenger inside, time flows normally. For the person on the platform, the passenger's time runs slow. That difference is not just an illusion. It is reality. It happens because both observers are slicing space-time differently. The stage and the clock are shifting together in order to keep the speed of light sacred. Space-time is not rigid. It can bend, stretch, warp. When something massive, like a planet or a star, is present, space-time curves around it. And here is where the story deepens. Einstein extended his theory of relativity into what we now call general relativity. In this grander theory, gravity is not a force pulling objects the way Isaac Newton imagined. Instead, gravity is the curvature of space-time itself. Imagine placing a heavy ball on a trampoline. The fabric dips under the weight. Smaller balls rolled across the surface curve toward the heavy one. Not because they are pulled by an invisible string, but because the surface itself guides their motion. That is space-time around a star or a planet. Light itself follows these curves. Starlight bends around the sun, creating illusions of stars being shifted in the sky. This bending was famously observed during a solar eclipse in 1919, providing the first dramatic confirmation of Einstein's theory. The speed of light remains the same, but the path it takes is shaped by the geometry of space-time. It is like walking across a hilly meadow. Your pace may not change, but the distance and the route certainly do. This is why astronomers see phenomena like gravitational lensing, where light from a distant galaxy is bent around another galaxy in between, creating arcs and rings of distorted light. Entire clusters of galaxies act like cosmic magnifying glasses, letting us peer deeper into the universe than we otherwise could. The speed of light is thus not just a limit. It is a tool for mapping the structure of reality. Every time we measure how light is bent, slowed, or delayed, we learn something about the shape of space-time itself. We see invisible matter, we weigh galaxies, we trace the unseen scaffolding of dark matter. Without the speed limit of light, without its obedience to the geometry of space-time, much of this cosmic cartography would be impossible. Now, think of black holes. These are the ultimate consequence of space-time's ability to curve. When enough mass collapses into a small enough region, space-time curves so steeply that nothing, not even light, can escape. The event horizon marks the boundary. Once crossed, all paths lead inward. Light, which normally races freely across the cosmos, becomes trapped. The speed limit is still there, but the path is so twisted that all routes fall inward. This reveals something profound. The speed of light is not simply a rule about motion. It is also the boundary between what is visible and what is hidden. Black holes remind us that even though light is fast, it is not invincible. Space-time itself can shape and redirect it, creating shadows, horizons, and mysteries that remain beyond our reach. And yet, even here, the constancy of light speed is crucial. Without it, black holes would not form as we understand them. The horizons would not exist. Gravity would not bend light in the same elegant way. The universe would lack these extraordinary laboratories where physics pushes against its own edges. Let us step back for a moment and consider how much this one constant does. It links electricity and magnetism. It gives us relativity. It sets the rhythm for time. It draws cones that map causality. It bends around stars. It hides inside black holes. It frames the very stage of existence. All of that from a single speed. It is humbling, and maybe also calming, to realize that something so fast and so constant is also so gentle in its consequences. It does not shout. It does not demand. It simply is. Every photon you see, every glimmer on water, every sunrise and candle flame obeys this rhythm. The speed of light is the quiet law written everywhere, never broken, never changing, and always guiding. So, when you next look at the night sky, remember that each point of light you see has traveled faithfully along space-time's curves at the only speed it knows. It has crossed gulfs of darkness, bent around stars, passed through interstellar clouds, all while keeping the same pace. In those beams, you are not just seeing brightness, you are seeing the universe honoring its most ancient rule. As we move deeper into the quiet mystery of light's unchanging pace, we begin to see how it does not only shape physics in the abstract, but also sets the rules for what kind of universe can exist at all. Imagine, for a moment, if the speed of light were different, faster, slower, or variable. The consequences would ripple through everything we know. Let us start with the idea of a faster light speed. Suppose light could travel infinitely fast. At first, it might seem convenient. You could see the entire universe at once. Communication would be instantaneous. Telescopes would reveal galaxies as they are right now, instead of billions of years in the past. But look closer. instant light would erase causality. Events could no longer be separated by time. You could know about an effect before the cause. A star could explode, and you might see the explosion before the star even formed. The logic of cause and effect would unravel. Without the light speed limit, time itself would lose meaning. Now, imagine a slower light speed. If light traveled, say, thousands of times slower, the universe would shrink in terms of what could connect. Even nearby stars might be invisible because their photons would not reach us in any reasonable span of time. The night sky would be dark and empty. Life might struggle to emerge at all, cut off from the warmth and energy of distant suns. The delicate balance of chemistry on Earth depends on sunlight streaming steadily across 150 million kilometers in just 8 minutes. Slow that down too much and the system collapses. And what if light speed varied depending on direction or location? Then the entire structure of relativity would collapse. Different observers could measure different constants, disagreeing not just about simultaneity but about the fundamental laws of physics. Science itself would lose coherence. The fact that light speed is the same for everyone, everywhere, is what allows us to write universal laws. It is what makes science work across time and space. This reflection reveals something profound. The universe as we know it requires light to travel at exactly this speed. Too fast, causality vanishes. Too slow, life and connection vanish. Too inconsistent, order vanishes. The value we measure is not random. It is a condition for reality as we experience it. Let us gently turn now to something even more astonishing. Quantum mechanics. At the smallest scales, particles behave not like tiny billiard balls but like probabilities, clouds of potential, shimmering with uncertainty. And yet, even here, light speed leaves its mark. No quantum signal, no entangled particle, no wave function collapse can transmit information faster than light. Entanglement might look instantaneous, but when tested carefully, it obeys the cosmic limit. The universe may play with probability, but it does not cheat on its speed. And this limit has become a guiding principle for modern physics. Theories of quantum fields, of dark matter, of dark energy, all build upon the certainty that light's pace is a ceiling. Even when we dream of unifying general relativity with quantum mechanics, the constant C stands in the center like a compass point. It defines the scales, the energies, the possible. Now let us wander into the realm of possibility. What about faster than light travel, the dream of science fiction? Warp drives, wormholes, hyperspace lanes. Could they exist? Physics tells us that nothing with mass can accelerate past light speed in normal space. But clever minds have wondered whether space-time itself could do the trick. If you cannot move through space faster than light, could you move space itself? This is the idea behind a warp drive. Compress space-time in front of a ship, expand it behind, and the bubble could move faster than light relative to distant observers without the ship itself, breaking the speed limit inside the bubble. In theory, the rules are not broken. In practice, the energy required is staggering, likely greater than the energy of entire stars. Wormholes offer another tantalizing idea: shortcuts through space-time. If such tunnels exist, they could connect distant regions instantly. But again, the mathematics demands exotic matter, negative energy, ingredients that we are not sure the universe provides. Even in our most daring dreams, the speed of light asserts itself. It is not casually overturned. It forces imagination to work harder, to bend space rather than to simply dash forward. In that way, the limit is not a wall but a horizon, pushing us to expand our thinking, and perhaps that is the final quiet lesson. The speed of light is not just a physical boundary, it is also an intellectual one. It teaches patience, it teaches humility. It reminds us that knowledge comes in beams, delayed, stretched, slowed, but always faithful. It tells us that the universe is not a place of shortcuts, but a place of steady unfolding. So tonight, as you drift toward rest, let this thought settle in you. The universe could have been chaos. It could have been noise without rhythm. Instead, it is ordered by a single number, steady and constant, a number that allows stars to burn, planets to orbit, atoms to bind, and life to wonder. The speed of light is not just a measurement. It is the silent rule that makes wonder possible, the bounder. As we approach the closing chapters of our journey with light, let us take a moment to imagine how this constant speed shapes not just science, but our very sense of place in the cosmos. Light is not only a number written into equations. It is the thread that ties together past, present, and future, and it defines the limits of what we can ever know. Consider the cosmic horizon. Because light takes time to travel, we can only see as far as light has had time to reach us since the beginning of the universe. The universe is about 13.8 billion years old, which means, in principle, the farthest light we can observe has been traveling for 13.8 billion years. But because space itself expands, the actual distance to those sources is much greater, tens of billions of light years. Still, there is a boundary, a horizon beyond which we cannot see. Not because our telescopes are weak, but because light has not had time to arrive. That horizon is written into the structure of the universe by light's constant pace. This horizon is not static. As time passes, more distant light arrives, expanding what we can see. At the same time, galaxies beyond a certain distance are receding so quickly due to cosmic expansion that their light will never reach us. They are crossing what is sometimes called the cosmic event horizon. Beyond that, the universe exists, but it is forever hidden. A permanent veil drawn not by distance, but by the limit of light speed combined with expansion. Think of what this means. We live in a universe where most of it will never be visible to us. Most galaxies, most stars, most stories are locked forever beyond our sight. And yet, within our observable bubble, we see enough to understand the great arcs of history, the birth of galaxies, the formation of stars, the emergence of planets, the slow dance of cosmic evolution. All of this because light has carried the information faithfully across unimaginable distances. Never faster, never slower, always steady. This constancy is also what allows cosmologists to reconstruct the early universe. By studying the cosmic microwave background, the faint afterglow left from when the universe was just 380,000 years old, we read a snapshot of the cosmos in its infancy. Those photons have been traveling ever since, stretched into microwaves by expansion, whispering to us about density, temperature, and the seeds of galaxies. Without the speed of light as a constant, this kind of archaeology of the universe would be impossible. The timeline itself would blur. Even more astonishing is how this single constant shapes the fate of the cosmos. If light could move faster, the expansion of the universe would reveal itself differently. If it could move slower, horizons would shrink and history would appear more compressed. But at exactly this pace, we glimpse enough to build models, to ask questions, to imagine futures. Let us also reflect on how the speed of light shapes human ambition. Every dream of interstellar travel is measured against this yardstick. When science fiction writers imagine journeys to distant stars, they grapple with the immensity of distances defined by light years. A light year is not just poetic. It is a measure of distance bound directly to the speed of light. The distance light covers in 1 year, about 9.46 trillion kilometers. A star 10 light years away means that even at the ultimate possible speed, it would take a decade to arrive. This is why interstellar travel is such a challenge. Even at 10% the speed of light, reaching the nearest stars would take decades, perhaps centuries. Generations might be born and die aboard such ships. Messages to and from those travelers would arrive with years of delay. And yet, the very difficulty makes the dream profound. It means that if humanity ever does voyage to other stars, it will not be a casual endeavor. It will be a commitment of patience, endurance, and faith. The speed of light does not crush our dreams. It shapes them. It forces us to think bigger, to value the journeys, not just the destinations. It turns exploration into a generational act, a weaving of humanity's story across time as well as space. And so, as we near the close of this meditation, let us return to the simple truth. Light moves at 299,792,458 meters per second in a vacuum, always, everywhere, for all observers. It is the heartbeat of physics, the rhythm of space-time, the metronome of causality. From lanterns on hillsides to satellites orbiting Earth, from Galileo's hopeful experiments to the equations of Maxwell and Einstein, humanity has chased this number across centuries. And in finding it, we have found something more, a glimpse of how reality itself holds together. The speed of light is not just a speed. It is the law that writes the story of time, the guardian of cause and effect, the bridge between matter and energy, the key to understanding the past and imagining the future. It is quiet, constant, patient, eternal. And because of it, the universe is not chaos. It is harmony. As we reach the final stretch of our journey with light, it feels right to gather the threads together, to see how one constant speed has guided us from the smallest particles to the largest structures of the cosmos. Light speed is not simply a number. It is a unifying principle, a law that sings quietly through every corner of physics. Through every story we have told tonight, we began with photons, those restless messengers of energy, massless yet eternal, vibrating as waves of electricity and magnetism. We watched humanity's attempts to measure their pace, from Galileo with lanterns to old Rachma with Jupiter's moons, from Fizeau's spinning wheels to Michelson's precise mirrors. Each step brought us closer to the realization that light speed is finite, measurable, and deeply woven into the universe. We saw how James Clerk Maxwell uncovered the number hidden in his equations, and how Albert Einstein showed us that it was more than just a speed. It was the foundation of relativity, the reason time can dilate, lengths can contract, and simultaneity can vanish. The speed of light forced us to see time and space not as separate, but as a fabric called space-time, bending and curving around stars, shaping orbits, guiding galaxies. We traced how this constant creates horizons, cones of cause and effect that define what can influence what. We saw how it allows telescopes to become time machines, capturing the faint light of galaxies billions of years away, carrying memories across cosmic history. We realized that our very knowledge of the Big Bang, of dark energy, of the universe's expansion, all rests upon the fact that light obeys one steady rule. We explored how E equals mc ties mass and energy together, turning stars into furnaces and releasing the light that sustains life on Earth. We pondered black holes, where light itself is trapped by space-time's curvature. And we marveled at gravitational lensing, where galaxies bend light into rings and arcs, giving us glimpses deeper than we should be able to see. We wondered what would happen if light speed were different to fast, too slow, too variable, and we saw how fragile reality would become. Without this constant, causality would break, life would falter, order would collapse. The universe is balanced upon this number. It is not arbitrary. It is essential. We even dared to imagine faster than light dreams, warp drives, wormholes, tunnels through space-time. Fascinating, enticing, but always demanding impossible energies or exotic matter. Even our dreams must bow to the constant. Even our most ambitious visions must acknowledge its authority. And so we return to where we began, light, traveling at nearly 300,000 kilometers per second, swift enough to circle Earth 7 times in a heartbeat, patient enough to cross interstellar gulfs for millions or billions of years. Each photon that enters your eye has obeyed this law without question. From the instant it was born in the heart of a star to the moment it ends its journey in your mind. There is something comforting in that. Something steady, something that tells us, even in a universe of change and chaos, there are constants we can trust. Light speed is one of them. So, as you drift now toward rest, let yourself imagine that rhythm. A universe where every star, every galaxy, every breath of time is guided by the same pace. Where the laws are not chaotic but harmonious, written in light. The speed of light is not just physics. It is a lullaby written into the cosmos. It whispers across time and space, carrying stories from the beginning to the present, and perhaps even to futures we cannot yet imagine. Tonight, as your eyes grow heavy, let that constancy be your anchor. Just as light never falters, never hurries, never slows, you too can rest in the assurance of something steady. The stars will shine, the galaxies will spin, the photons will fly, and all of it will move to the same unchanging rhythm. The universe holds you gently in its laws, and light, patient and eternal, will always be there to guide your dreams.